Hello. And welcome back to the Umbrella Academy. In many cases, E2 elimination reactions are regioselective and can produce more than one product. Consider this alkyl halide. There are two non-identical beta positions with respect to alpha carbon connected to leaving group bromine. So the double bond can form in two different regions of the molecule. This consideration is an example of regiochemistry, and the reaction is said to produce two different regiochemical outcomes. Both products are formed, but for reasons of molecular stability, the more substituted alkene is generally observed to be major product. This alkene is trisubstituted and is called Zaitsev product. Because this trend was first observed by Russian chemist Alexander M. Zaitsev. This is of course more stable. The minor product is disubstituted alkene and is called Hofmann product. This is less stable. The Zaitsev product being more stable is major product under normal conditions. Whereas the Hofmann product being less stable is major product only under special conditions. First is when base is bulky. Second, when leaving group is poor, such as fluoride anion, ammonium or sulfonium groups. Third is when there is steric hindrance at beta carbon. Fourth is when the Hofmann product is a conjugated alkene. Before going into the details of these conditions, let me tell you that Zaitsev product is major product in the above reaction, because product as well as transition state leading to the product is more stable, or we can say lower in energy. For example, consider this transition state leading to 2-butene and 1-butene. Because the transition state has an alkene-like structure, the transition state leading to the 2-butene is more stable than the transition state leading to 1-butene, for the same reasons that 2-butene is more stable than 1-butene. The more stable transition state allows 2-butene to be formed faster than 1-butene. In the energy profile diagram, you can clearly see that difference in the rate of formation of the two alkene products is not very great, so both products are formed, but the more stable alkene is the major product of elimination reaction. Now let us discuss the conditions that favor Hofmann product to be the major product. First is the use of bulky base. Consider the previous elimination reaction of 2-bromo-2-methylbutane. With ethoxide base, Zaitsev product is the major product, as we have just seen. However, with tertiary butoxide and higher alkoxides, the Hofmann product is found to be the major product. This clearly shows that the regiochemical outcome of an E2 reaction can often be controlled by carefully choosing the base. The reason for this change in regioselectivity is that a large, highly branched base preferentially attacks on the least sterically hindered beta hydrogen to form stable transition state. In this case, stability of transition state depends mainly on steric hindrance and not on the alkene character. Abstraction of less substituted beta hydrogen by bulky base gives less substituted Hofmann product as the major product. Second condition is when there is a poor leaving group like fluoride anion. In case of chloride, bromide and iodide leaving groups, the halogen starts to leave as soon as the base begins to remove the proton. Departure of the halogen and its bonding electrons prevents the buildup of negative charge on the carbon that is losing a proton, giving the transition state alkene character rather than carbanion character. Of the halogen ions, the fluoride ion is the strongest base, and hence very poor leaving group. So, when a base begins to remove a proton from the beta carbon of alkyl fluoride, the fluoride ion has less tendency to leave than do the other halide ions. As a result, negative charge develops on the beta carbon that is losing a proton, giving the transition state a carbanion character rather than an alkene character. This carbanion transition state is stabilized by the strong electron withdrawing group fluorine. Thus, transition state leading to Zaitsev product develops carbanion character on secondary carbon, which is less stable than the transition state leading to Hofmann product, where carbanion character develops on primary carbon, and is comparatively more stable. Thus, when alkyl fluoride is treated with methoxide base, Hofmann product is major product in this case, as it is formed from the more stable transition state. On the similar grounds, one can explain why the compounds having ammonium or sulfonium groups as leaving groups give Hofmann elimination. Third condition is crowding at beta carbon. If the beta carbon, whose abstraction by base would lead to Zaitsev product, is hindered, then the less hindered beta hydrogen leading to Hofmann product is preferred by base. For example, consider this alkyl bromide. It has two different beta hydrogens. These red beta hydrogens are bonded to secondary carbon, and these green beta hydrogens are bonded to primary carbon. These secondary beta hydrogens are sterically hindered, and their elimination with bromine gives this more substituted alkene. The elimination of less substituted green hydrogen with bromine gives this less substituted alkene. Thus crowding at secondary beta hydrogen forces the base to abstract primary beta hydrogen so that in the end, Hofmann product is the major product. The fourth condition favoring Hofmann product is when it is conjugated. If the substrate contains one or more double bonds, then that beta hydrogen is preferred by base, which leads to conjugation in the product. Consider this alkyl bromide substrate. It has secondary beta hydrogen shown in red color and tertiary beta hydrogen shown in green color. The abstraction of red hydrogen gives this less substituted alkene product, whereas abstraction of green hydrogen gives this more substituted alkene product. We call this Hofmann and this as Zaitsev product. In the Hofmann alkene new double bond is conjugated with phenyl ring, whereas in Zaitsev product new double bond is isolated. Therefore Hofmann product is major because it is conjugated and more stable product than Zaitsev product, which is an isolated alkene and hence less stable and minor product in this case. Consider this cyclic substrate. With respect to chlorine substituent, there are three beta positions. This beta carbon doesn't have any hydrogen. Thus, only two types of beta hydrogens are available and hence two products will be formed. Removal of beta hydrogen from ring gives this cyclic alkene, and removal of beta hydrogen from exo-methyl gives this exo-cyclic alkene. This alkene is more substituted and hence Zaitsev product. This alkene is less substituted and hence Hofmann product. Zaitsev product will be major and Hofmann minor product. Consider this alkyl halide treated with potassium tertiary but oxide base. This is a bulky base. Substrate has three beta positions. The two beta positions inside the cyclic ring are similar. Tertiary but oxide is sterically hindered base, and will therefore prefer less sterically hindered beta hydrogen for abstraction to form Hofmann product as major product. Thus, removal of any of the secondary beta hydrogens from the cyclic methylene gives this alkene with double bond inside the ring, while the removal of primary hydrogen of methyl gives this exocyclic alkene. This cyclic alkene is more substituted and this exocyclic is less substituted. Thus, this is the minor and this is the major product upon treatment with bulky base. Consider the elimination of this cyclic chloride. This is called methyl chloride. It has two beta carbons. This beta carbon has isopropyl group on wedge, therefore hydrogen must be on dash. Similarly, this beta carbon has two hydrogens. Let us put cyan blue hydrogen on wedge and red hydrogen on dash. This chlorine on alpha carbon is cis to this red beta hydrogen and this white hydrogen, because both of these are also on dash. This chlorine on dash is trans to this cyan blue hydrogen on wedge. Therefore this will be eliminated on treatment with base to form this alkene product. Only one beta hydrogen is anti-periplanar to chlorine, therefore only one E2 product is possible. Take the similar isomeric molecule with chlorine cis to isopropyl group, both shown on solid wedge here. This is called neomethyl chloride. Thus, hydrogen on this beta carbon must be on dash. The other beta carbon has two hydrogen, cyan blue shown on solid wedge and red one, shown on dash. This chlorine and this cyan blue hydrogen, both are on solid wedge, which means they are cis to each other, and hence it cannot be eliminated with chlorine. This red and white hydrogen on dash are trans to this chlorine on wedge, and hence, both can be eliminated with chlorine to form two different alkene products. Elimination of white hydrogen with chlorine gives this alkene, and that of red hydrogen gives this alkene. This is more substituted, and this is less substituted. This is Zaitsev product, and this is Hofmann product. Zaitsev product, of course, will be major, and Hofmann will be minor product. If you don't want to miss out important lectures, then subscribe and press bell icon for notifications of new lecture uploads.